Hi, and welcome to the Machine Learning Pico degree from Udacity. So what we're going to talk about today is what is machine learning? Well, this is the world, and in the world we got humans and we got computers. And one of the main differences between humans and computers is that humans learn from past experience, whereas computers need to be told what to do. They need to be programmed, so they follow instructions. Now the question is, can we get computers to learn from experience too? And the answer is yes, we can. And that's precisely what machine learning is. Of course, for computers, past experiences have a name. It's called data. So in the next few minutes, I'm going to show you a few examples in which we can teach the computer how to learn from previous data. And most importantly, I'm going to show you that these algorithms are actually pretty easy and that machine learning is really nothing to fear. So let's go to the first example. Let's say we're studying the housing market and our task is to predict the price of a house given its size. So we have a small house that costs $70,000. We have a big house that costs $160,000. And we'd like to estimate the price of this medium-sized house here. So how do we do it? Well, first put them in a grid where the x-axis represents the size of the house in square feet and the y-axis represents the price of the house in dollars. And so to help us out, we have collected some previous data in the form of these blue dots. These are other houses that we've looked at and we've recorded their prices with respect to their size. So in this graph, we can see that the small house is priced at $70,000 and the big house is priced at $160,000. So now it's time for a small quiz. What do you think is the best guess for the price of the medium house given this data? Would it be $80,000, $120,000, or $190,000? Well, to help us out, we can see that these blue points kind of form a line, so we can draw the line that best fits the data. Now on this line, we can say that our best guess for the price of the house is this point over here, which corresponds to $120,000. So if you said $120,000, that is correct. This method is known as linear regression. Now you may ask, how do we find this line? Well, let's look at a simple example. These 3 points. We're going to try to find the best line that fits through those 3 points. Obviously, best line is subjective, but we try to find a line that works well. Since we're teaching the computer how to do it, the computer can't really eyeball the line, so you have to get it to draw a random line and then see how bad this line is. So in order to see how bad the line is, we calculate the error. So we're gonna, for calculating the error, look at the lengths of the distances from the line to the 3 points. And we're gonna simply say that the error of this line is the sum of those 3 red lengths. Now, what we're gonna do is move the line around and see if we can reduce this error. So let's say we move it in this direction and we calculate the error. It's given by the yellow distances. We add them up and realize that we've increased the error, so that's not a good direction to go. Let's try moving the other direction. We move it here, calculate the error. Now it's given by the sum of these 3 green distances. And we see that the error is smaller, so we actually reduced it. So let's say we take that step. We're a little closer to our solution. If we continue doing this procedure several times, we will always be decreasing the error and we'll finally arrive to a good solution in the form of this line. This general procedure is known as gradient descent. Now in real life, we don't want to deal with negative distances corresponding to a point being on one or the other side of the line. So what we do to solve this is add the square of the distance from the point to the line instead. And this procedure is called least squares. So we can think of gradient descent as trying to descend from a mountain. This is our mountain, Mount Everest. In this mountain, the higher we are, the larger our error is. So descending means reducing the error. So what do we do when we try to descend the mountain? Well, we'll look at our surroundings and try to figure out which way we can descend more. For example, here we can go in 2 directions, to the right or to the left. If we go to the left, then we're going up, which means our error is ascending. This is equivalent to moving the line downwards and getting farther from the 3 points. But if we go to the right instead, then we're actually descending, which means our error is decreasing. This is equivalent to moving the line upwards and getting closer to the 3 points. So we decide to take a step towards the right. Then we can start this procedure again and again and again until we successfully descend from the mountain. This is equivalent to reducing the error until we find its minimum value, which gives us the best line fit. So you can think of linear regression as a painter who will look at your data and draw the best fitting line. Now this method is actually much stronger. If the data doesn't form a line, with a very similar method we can draw a circle through it, or a parabola, or even a higher degree curve. For example, the data here, we can actually fit a cubic polynomial. Okay, so let's move to the next example. In this example, we're going to build an email spam detection classifier. So something that will tell us if an email is spam or not. And how do we do this? We do this by looking at previous data. The previous data is 100 emails that we've looked at already. Out of these 100 emails, we have flagged 25 of them as spam and 75 of them as not spam. Now let's try to think of features that spam emails may be likely to display and analyze these features. So one feature could be containing the word cheap. It seems reasonable to think that an email containing the word cheap is likely to be spam. So let's analyze this claim. We look for the word cheap in all these 100 emails and find that 20 out of the spam ones and 5 out of the non-spam ones contain that word. So we can forget about all the rest of the emails and focus only on the ones that contain the word cheap. Okay, so time for a quiz. Here's the question. Based on our data, if an email contains the word cheap, what is the probability of this email being spam? Is it 40%, 60%, or 80%? Well, to help us out, we can see that out of the 25 emails with the word cheap, 20 of them are spam, while 5 of them are not. So these form an 80-20 split. So the correct answer was 80. If you said 80, you were correct. So from analyzing this data, we can conclude a rule. The rule says if an email contains the word cheap, then we're going to say that the probability of it being spam is 80%. So we then associate this feature with the probability 80%, and we're going to use it to flag future messages as spam or not spam. We can also look at other features and try to find their associated probability. Let's say we look at emails containing a spelling mistake and realize that the probability of an email containing a spelling mistake being spam is 70%. Or let's say we look at emails that are missing a title and find that the probability of those being spam is 95%, etc., etc. So now when future emails come, we can combine these features to guess if they're spam or not. This algorithm is known as the naive Bayes algorithm. Okay, so now another example. We are the App Store, or Google Play, and our goal is to recommend apps to users. So to each user, we're going to try to recommend them the app that they are most likely to download. We have gathered a table of data that we're going to use to make the rules, and the table contains 6 people. For each one of those 6 people, we have recorded their gender and their age and the app they downloaded. So for example, the first person is a 15-year-old female and she downloaded Pokemon Go. So here's a small quiz. Between gender and age, which one seems like the more decisive feature for predicting what app will the users download? Well, to help us out, first let's look at gender. If we split them by gender, then the females downloaded Pokemon Go and WhatsApp, whereas the males downloaded Pokemon Go and Snapchat. So not much of a split here. On the other hand, if we look at age, we realize that everybody who's under 20 years old downloaded Pokemon Go, whereas everybody who is 20 or older didn't. That's a nice split. So the feature that best splits the data is age. Therefore, if you said age, that was correct. So what we're going to do is we're going to add a question here. The question is, are you younger than 20? If yes, then we'll recommend Pokemon Go to you. If not, then we'll see. So what happens if you're 20 or older? Then we look at the gender. It seems like here, if you're a female, you've downloaded WhatsApp. Whereas if you're a male, you've downloaded Snapchat. So we add another question here. The question is, are you female or male? And if you're female, we recommend WhatsApp. And if you're male, then we recommend Snapchat. So what we end up here is with a decision tree. And the decisions are given by the question we ask. And this decision tree was built with the data. And now whenever we have a new user, we can put them through the decision tree and recommend them whatever app the tree suggests us to recommend. For example, if you have a young person, you recommend them Pokemon Go. If you have an older person, you check their gender. If it's a female, you recommend them WhatsApp. And if it's a male, you recommend them Snapchat. Obviously, there won't always be a tree that perfectly fits our data. But in this class, we're going to learn an algorithm which actually will help us find the best fitting tree to a table of data. Okay, so let's go to the next example. Now let's say we're the admissions office at a university and we're trying to figure out which students to admit. We're going to admit them or reject them based on two pieces of information. One is an entrance exam that we provide them, the test, and the other one is their grades from school. So for example, here we have student 1 with scores of 9 out of 10 in the test and 8 out of 10 in the grades. And that student got accepted. We also have student 2 with scores of 3 in the test and 4 in the grades, and that student did not get accepted. And then a new student comes in, student 3. This person has scores of 7 and 6, and the question is, should we accept them or not? So let's first put them in a grid, where the x-axis represents their score on the tests and the y-axis represents their grades. Here we can see that student 1 would lie over here in the point with coordinates 9, 8, since their scores were 9 and 8. And the student 2 would lie over here in the point with coordinates 3, 4, since their scores were 3 and 4. So in order to see if we should accept or reject student 3, we should try to find a trend in that data. So we look at the previous data in the form of all the students we've already accepted or rejected. And it turns out that the previous data looks like this. The green dots represent students that we've previously accepted, and the red dots represent students that we've previously rejected. So time for a quiz. Based on the previous data, do we think student 3 gets accepted, yes or no? So to answer this question, let's look closely at the data. The red and green dots seem to be nicely separated by a line. And here's the line. And most of the points over it are green, and most of the points under it are red, with some exceptions. Which makes sense, since the students who got high scores are over the line and they got accepted, and the students who got low scores are under the line and they didn't get accepted. So we're going to say that that line is going to be our model. And now every time we get a new student, we check their scores and plot them in this graph, and if they end up over the line, we predict that they'll get accepted, and if they end up below the line, we predict that they'll get rejected. So since student 3 has grades of 7 and 6, that person will end up here at the point 7.6, which is over the line, so we conclude that this student gets accepted. So if you said yes, that's the correct answer. This method is known as logistic regression. And now the question is, how do we find this line that best cuts the data in two? So let's look at a simple example. These 6 points, 3 green, 3 red, and we're going to try to draw a line that best separates the green points from the red points. And again, a computer can't really eyeball the line, so it can just start by drawing a random line like this one. And given this line, let's just randomly say that we label the region over the line as green and the region under the line as red. So just like with linear regression, we're going to try to see how bad this first line is. And the measure of how bad the line is would be how many points are we misclassifying. We're going to call that number of misclassified points the error. This line, for example, misclassifies 2 points, one red and one green. So we'll say that it has 2 errors. So again, like with linear regression, what we'll do is move the line around and try to minimize the number of errors using gradient descent. So if we move the line a bit in this direction, we can see that we start correctly classifying one of the points, bringing down the number of errors to 1. And if we move it a little more, we will correctly classify the other one of the points, bringing down the number of errors to 0. In reality, since we use calculus for our gradient descent method, it turns out that the number of errors is not what we need to minimize, but instead something that captures the number of errors, called the log loss function. And the idea behind the log loss function is that it's a function which assigns a large value to the misclassified points and a small value to the classified points. Okay, so let's look more carefully at this model for accepting and rejecting students. Let's say we have a student 4 who got 9 in the test and 1 on the grades. So this student gets accepted according to our model since they are over here on top of the line. But that seems wrong, since a student who got very low grades shouldn't get accepted no matter what their test score was. So maybe it's too simplistic to think that this data can be separated by just one line, right? Maybe the real data should look more like this, where these students over here who got a low test score or low grades don't get accepted. So now it seems like a line won't cut the data in two. So what's the next thing after a line? Maybe a circle? A circle could work. Maybe 2 lines? That could work too. Actually, that looks like that works better, so let's go with that. Now the question is, how do we find these 2 lines? Again, we can do it using gradient descent to minimize a similar log loss function as before. This is called a neural network. Now, why is it called a neural network? Well, let's see. We have this green area here bounded by 2 lines. This area can be constructed as an intersection, namely the intersection between the green area on top of one of the lines and the green area to the right of the other one of the lines. So we're going to graph it like this. We have 2 nodes. Each node is a line that separates the plane into 2 regions, and from the 2 nodes we get the intersection, which is the desired area. The reason why this is called a neural network is because this mimics the behavior of the brain. In the brain, we have the neurons, which connect to each other, and they either fire electricity or not. They resemble the nodes in our graph, which split the plane into regions and fire electricity if a given point belongs to one of those regions and won't fire if it doesn't. So we can think of linear regression as a ninja who will look at your data and cut it in half based on the labels. And we can think of a neural network as a team of ninjas who will look at your data and cut it into regions based on the labels. Okay, so let's dive a bit deeper into the art of splitting data into 2. We can look at these points, 3 green and 3 red. And there seem to be many lines that can split them. For example, there is this yellow line. And there is this purple line. So quiz, which of these 2 lines do we think cuts the data better? The purple one or the yellow one? Well, if we look at the yellow line, it seems that it's close to failing. It's too close to 2 of the points. So if we were to wiggle it a little bit, we would misclassify some of the points. The purple one, on the other hand, seems to be nicely spaced and as far as we can from all the points. So it seems like the best line is the purple one. Now the question is, how do we find the purple line? Well, the first observation is that we don't really need to worry about these points because they're too far from the boundary. So we can forget about them and only focus on the points that are close. And now, what we're going to use is not gradient descent, but we're going to use linear optimization to find the line that maximizes the distance from the boundary points. This method is called a support vector machine. So you can think of support vector machines as a surgeon who will see your data and cut it. But before, she will carefully look at what's the best way to separate the data in two and then make the cut. Okay, so now let's say we have these 4 points arranged like this and we want to split them. It seems like a line won't do the job since they're already over the line and the red ones are on the sides and the green ones are in the middle. So we need to think outside the box. One way to think outside the box is to use a curve like this to split them. Another one is to actually think outside the plane and to think of the points as lying in a three-dimensional space. So here are the points over the plane, and here we add an extra axis, the z-axis for the third dimension. And if we can find a way to lift the two green points, then we'd be able to separate them with a plane. So what seems like a better solution? The curve over here or the plane over here? Well, it turns out that these two are actually the same method. Don't worry if it seems confusing, we'll get into a little bit more detail later. This method is called the kernel trick and is very well used in support vector machinists. So let's study one of them in more detail. Let's start with the curve trick. So let's start by putting coordinates on the points. This one is a point 0, 3, this one is 1, 2, this one is 2, 1, and this one is 3, 0. And what we need is a way to separate the green points from the red points. So if the points coordinates are x, y, then we need an equation on the variables x and y that gives us large values for the green points and small values for the red points, or vice versa. So, quiz. Which of the following equations could come to our rescue? X plus y, the product x times y, or x squared, the first coordinate squared. This is not an easy question, so let's actually make a table with the values of these equations on each of the 4 points. So here's our table. Here we have the 4 points on the top row, and now each of the other rows will be one of the functions. So here's the sum x plus y. We fill in the first row in the following way. 0 plus 3 is 3, 1 plus 2 is 3, 2 plus 1, 3, 3 plus 0, 3. Now for the second row, we're going to get the products. 0 times 3 is 0, 1 times 2 is 2, 2 times 1 is 2, and 3 times 0 is 0. And for the third row, x squared is the first coordinate square, so 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. So let's think, which one of these equations separates the green and the red points? We look at the sum x plus y, and that gives us 3 at every value, so it doesn't really separate the points. We can look at x squared, and that gives us different values for every point, but we get 0 and 9 for the red values and 1 and 4 for the green ones, so this one also doesn't separate them. But now we look at the product x times y, and that gives us 0 for the red values and 2 for the green ones. So that one seems to do the job, right? It is a function that can tell them apart. So that's the equation we're going to use. You can see the products here. And now, for the red points x comma y, we have that the product xy equals 0. And for the green points, we have that the product xy equals 2. And what separates a 0 and a 2? Well, a 1. So the equation xy equals 1 will separate them. And what is xy equals 1? It's the same as y equals 1 over x. And the graph for y equals 1 over x is precisely this hyperbola over here. That is the curve we wanted. So that is the kernel trick. Now we can also see it in 3D here. We have the points 0, 3, 1, 2, 2, 1, and 3, 0. And we're going to consider them in 3 space. So we're going to take the map that takes the point x comma y to x comma y comma x times y. So where does 0, 3 go? 0, 3 goes to 0, 3, 0, since the product of 0 and 3 is 0. 1, 2 goes to 1, 2, 2, so it goes all the way up, since the third coordinate is the height. The point 2, 1 also goes to 2, 1, 2. And the point 3, 0 goes to 3, 0, 0. So there we go. We can split them using a plane. So you can think of a support vector machine kernel method as a surgeon who is slightly confused trying to split some apples and oranges. All of a sudden she comes up with a great idea. The idea consists of moving the apples up and the oranges down, and then successfully cutting a line through between them. Okay, so let's move to the next example. Let's say we have a chain of pizza parlors and we want to put 3 of them in this city. So we make a study and realize that the people who eat pizza the most live in these locations. And so we need to know where are the optimal places to put our 3 pizza parlors. Well, it seems like the houses are nicely split into 3 groups, the red, the blue, and the yellow. So it would make sense to put 1 pizza parlor in each one of the 3 clusters. But we're teaching a computer how to do this, and a computer can't just eyeball the 3 clusters. We need an algorithm. So here's one algorithm that will work. Let's start by choosing 3 random locations for the pizza parlors. So they're here where the stars are located: red, blue, and yellow. Now it would make sense to say each house should go to the pizza parlor that is closest to it. In that case, we can look at the map like this, where the yellow houses go to the yellow pizza parlor, the blue houses go to the blue pizza parlor, and the red houses go to the red pizza parlor. But now, look at where the yellow houses are located. It would make a lot of sense to move the yellow pizza parlor to the center of these houses. Same thing with the blue houses and the red houses. So let's do that. Let's move every pizza parlor to the center of the houses that it serves, as follows. But now, look at these blue points. They're a lot closer to the yellow pizza parlor than to the blue one, so we might as well color them yellow. And look at these red points. They're closer to the blue pizza parlor than to the red, so let's color them blue. And now, let's do the step again. Let's send each pizza parlor to the center of the houses that it's serving, in this way. But then again, look at these red houses. They're so much closer to the blue pizza parlor, so let's turn them blue. And then again, let's move every pizza parlor to the center of the houses it serves. And now we've reached an optimal solution. So starting with random points and iterating this process helped us reach the best locations for the pizza parlors. This algorithm is called k-means clustering. But now let's just say we don't want to specify the number of clusters to begin with. Let's use a different way to group the houses. So say they're arranged like this. It would make sense to say the following. If 2 houses are close, they should be served by the same pizza parlor. So if we go by this rule, let's try to group the houses. Let's look at which houses are the closest to each other. It's these 2 over here. So we group them. Now what are the next 2 closest houses? It's these 2 over here, so we group them. The next 2 closest houses are these 2, so again we group them. The next 2 closest houses are these 2, so we unite the groups. Now the next 2 houses are here, so we group them. The next 2 closest houses are here, so we join the groups. The next 2 closest houses are here, but now let's just say that's too big. So all we need to do is specify a distance and say this distance is too far. When you reach this distance, stop clustering the houses. And now we get our clusters. This algorithm is called hierarchical clustering. So congratulations! In this video we've learned many of the main algorithms of machine learning. We learned to find house prices using linear regression. We learned to detect spam email using naive Bayes. We learned to recommend apps using decision trees. We learned to create a model for an admissions office using logistic regression. We learned how to improve them using neural networks. And we learned how to improve it even more using support vector machines. And finally, we learned how to locate pizza parlors around a city using clustering algorithms. So many questions may arise in your head, such as, are there more algorithms? The answer is yes. Which ones to use? That's not easy. Given a data set, how do we know which algorithm to pick? How to compare them and evaluate them? Given two algorithms, how do you know which one is better than another one on a data set? Given their running time, their accuracy, etc. Are there examples? Are there projects? Are there real life data that I can get my hands dirty with them? The answer to all these questions and more are in the Udacity Machine Learning Nano degree. So if this interests you, you should take a look at it. Thank you.